everyone, and welcome back to this series of application of machine learning using WEKA in Power Asset Assessment. And today we will talk about a very important topic in application of machine learning, and this will be the feature reduction. So far, we in the examples I mentioned to you, we have certain feature vector. We don't touch it. We use it as it is. Okay, and we never study the impact of changing, removing some of the features. Are all the features important or not? We never study that. So today we will just touch a little bit of base on the is all the features are important, or do we need all of them? Can we remove some of them, and so on and so forth. So the first thing is something very important, that not all features are important. This is a fact. Okay, some features are highly correlated with the classes or whatever you want to predict, and some features they are not. And I will give some example in the coming slides. Okay, the second thing, that some features are redundant, meaning that if you remove one and keep the other, they will do exactly or almost the same job. So we don't need to have all of them. And also, when we have too many features, this will lead to very long computational time. So from different aspects, sometimes improving the accuracy, sometimes reducing the computational time, and sometimes also we want to reduce the feature vector for some practical applications. I will come to it into the example. This is why feature reduction is something very, very important. And anyone who works with machine learning, he or she needs to look into this, into the features closely, and select the best feature. Now, this is a very advanced, could be very advanced topic in machine learning. There are many sophisticated techniques in feature selection, like using PCA or using stepwise regressions and many other highly mathematical approaches. That's not the objective of this lecture, and that's not the objective of the whole series. We don't want to go to the math. We just want to try to present the concept, understand it without the need to go to the details of the complications of the math. So to demonstrate this, I selected this example. This example, we did it in the first series, which is the prediction of the IFT as a class. Okay, so if you recall, we have three classes: good and medium or moderate and bad. And we have this feature vector. We have water, acidity, breakdown voltage, dissipation factor, and color. The question is, do we need all these features? Can we reduce? Now, why we need to reduce? It's very obvious. Now, I want to predict IFT. If I can reduce the number of tests, will reduce my cost. I don't need, if the objective is to find the IFT, I don't need to have all these 5 tests. Maybe I need 2 or 3 of them, and will give me a very similar result. So it has some practical applications. The second question is, am I including some features that really impact in a negative way my prediction? And this is also something that we want to investigate. So just this is a recap. What we did before: we applied ANN, we applied SVM, we applied KNN5, and we applied J48. This is features. We applied them again in a previous video, and I will put the link in that video in case you don't know where is it, so that you can go and watch this. Okay, so here we achieved this is 91.5, 90.13, 90.13, and 90.5. So this is what we achieved. Okay, now I used a very basic technique to tell you the importance of each feature, which is the correlation matrix. So here, how these features are correlated with each other. So when we have one, this is like perfect correlation. Okay, now as this number is reduced going to 0, this is bad. Now you could have a high positive number or a high negative number. The maximum you can get is between +1 and -1. So this is your range. Now, if what +1 means, we have perfect correlation. As one increase, the other also increase. What is -1? Again, this is a perfect correlation. As one increase, the other decreases. Okay, and in between now is different values, and of course this is you will not achieve this except if you check the correlation of the feature with itself. So this is the water with the water, you get 1. This is perfect. Acidity with acidity, it's 1. So this diagonal, you'll see all these ones because it shows the correlation of the feature with itself. Okay, excellent. Now we want to see with the IFT how these features are correlated. So the water is minus 0.36, which is in the negative, meaning that as the water content increases, the IFT decreases, and that makes sense from the physics point of view. High water content is bad, and this will impact the IFT. Acidity, same thing, but the acidity, as you can see here, has a much higher number, around double. So you expect that the acidity to be a much better feature than the water. The BDV is the worst among all the features. It's 0.092. The DF is similar to the acidity. The highest is the color, okay, which is minus 0.88. Now, what we want to do now, I will recall the same data, and then I will start to add some of the features and see what is the impact of this on the accuracy, and see how, for example, removing something like the BDV will not impact in a negative way, or should not impact in negative with the accuracy. Maybe even the opposite, maybe even removing the BDV is better for us, will lead to improving the accuracy. However, removing a feature like the color will impact the accuracy in a very negative way. So this is a very simple technique. It tells you the importance of each feature with respect to what you want to predict. So now let's go to our WEKA. So let's start as we used to do. Let's open the file. So we go to get the data from here. So we will get just one simple data, the same data I showed the results, which is the IFT data classification 3 class. Okay, now I will select the KNN5. This is just an example. Okay, so we will classify and we'll choose KNN5. I could use any of them, but this is just to demonstrate for you. So this is under the lazy. This is the IPK or the KN5, and I will choose this as 5. Okay, start. So this is the 90.137 that I showed you in the slides. This is what we achieved with full features. Okay, now let's go back here. And here, one of the advantages of WEKA, you can remove the features using the software itself. You don't need to go and change the file. So what I want to remove, I will remove the BDV, which is the breakdown voltage, because this shows the lowest number of correlation. Okay, so you select here and then you say remove. Okay, now your feature vector has changed. You go to classify and everything is there. You just say start. Very simple. Now what you see here, there is an improvement. So I remove the feature. I'm getting a 91.6. So it is around 1.5% improvement, which is something really good. Okay, so I reduced one feature, meaning I'm reducing one test, meaning I'm reducing my cost. Not that only, but I'm improving also the accuracy. Okay, so the BDV shouldn't be there actually as a feature vector. Let's go back. Let's undo this. When you undo, okay, now let's remove both the BDV and the water. The water has higher, around minus 0.36, so it has some influence, so it might affect. So when you remove, let's remove both of them, and let's do the classify and start. So here it's 91.6, start. So at 91.4, not much, still better than having all the 5 features. So again, I can remove the water, and still I am getting some reasonable good results. Let's go back now. Let's undo all these things. Let's undo this change. And now let me remove the color and see the impact of removing the color, which has the highest correlation coefficient. Classify and start. And you can see here a drop around 5% or 4% drop in the accuracy. Okay, so that demonstrates to you that the IFT, sorry, the color is important to the prediction of the IFT. Now, why we don't have even more severe? Because the other features are there still, which they are also correlated with the color. So now if you go back here and you see the acidity with the color, it has high correlation, 0.74. Okay, so if I remove the color, still some of this correlation is, or some of this feature is embedded in the acidity. Same thing for the DF, it has 0.71. So when I remove the color, I don't completely remove the feature, because there is within the features there is some sort of correlation. So I hope this presentation showed to you the importance of feature reduction, why you are doing it, and give you some more insight about the importance of properly selecting the feature to get the best result.